Okay, I mean, it's a good comment.
What was that question?
The question was, the Hessian spectrum didn't look like it had the spectral signature of the transitions in it. But buried in that mess there's some stark shifting going on in that clouded it. So if you lower the intensity, you'll in fact see it looks like a 2D spectrum, basically. So here's the Hessian spectrum at the top, and you can count. You see the 6 negative eigenvalues. It's shifted up sort of to be away from this point. It's not exactly flat. It's 0. So this is the null space. Not exactly 0 but close. And here's the bottom. You see the 2 positive eigenvalues and this null space at the bottom. And indeed, this is really a very good affirmation that the theoretical principles are right. Well, of course, we have access to the eigenvectors. So we can pick an eigenvector in the null space here, or null space here, or the eigenvectors associated with these eigenvalues and those, and move along them. So on the top of the landscape, if we pick an eigenvector that's in the null space, you drive along, and the field is literally warping as you drive along, and you stay at the top. And as you successively move along the eigenvectors plus and minus direction, with larger and larger negative eigenvalue, fall off more and more rapidly. In fact, if you follow the largest negative one, you almost come to the bottom. Similarly, at the bottom of the landscape, you can drive along the bottom, not a place you'd like to be, but you could, or drive up. And there's 2 ways to come up. And of course, this is a little bit of a bastardization of what Feynman said, but indeed there is a top at the bottom of the landscape. Okay. So let's come back to this. And I said, learning, quantum control, chemistry, learning from each other. So I just gave you an example with the NMR chemical shift, where I think it's fair to say that we learned conceptually how to deal with that discrete problem which befuddled people in chemistry using principles, concepts from the quantum control landscapes. And here's this wonderful picture graph from chemistry, and a very basic question is there an analog of this on the photonic reagent side? So this is chemical reagents attacking substrate. So chemistry is full of that kind of story. You ask what a photonic reagent is. When I say, okay, is there an analog of photonic reagents attacking substrates like this? And do we see a systematic story like this? And here's where we can learn from the chemistry community. So these adaptive control experiments, there's about 50 labs around the world involved in experiments in this area. And as I told you, they're dispersed over about 20 different classes of applications, and everybody has their own interest. So there are not a lot of experiments in any area, and until now there has been no obvious pattern, because you need to do a lot of experiments in a related family, and that's what chemists do, and that's what we decided we'd take a shot at Princeton. And to answer this question, we really need to look at large numbers of experiments on what are called homologous families, in other words, molecules that are related to each other. That's the game of the goose over here. So we did this using polynomial phase variables. Now actually we did this to start with 80 pixels on the pole shaper, but I can't show you graphs in 80 dimensions. And then we switched to this basis, which is believed to be a reasonable basis in any problems. And it worked close to as well as the 80 pixels in terms of yield. So, and I can show you graphs of it, so this is what we'll stick with. So A, B, and C are the controls, these coefficients. And this is just a picture of a hull shaper. I'll show you a picture later when I have time at the end. So here's what we picked as a family. These are halomethanes. In other words, halogenated methane, chloromethane, dichloromethane, and so forth. And there's about 80 of them, or 60 of them that exist, of which about a dozen you can buy easily, and that's why we stopped here. They're ordered just by the ionization potential of the molecules. And we fire off or burn to optimize laser pulses for different objectives. And one of them, is some activist that was historically always on the table in the chemical reaction game with lasers, is to break the strong bond and not the weak bond. So for example, the fluorine-carbon bond is stronger than the fluorine-carbon bond. So what we record is pulling off the fluorine and then the ionization of fluorine. The signal recorded in the mass spectrometer, a high vacuum chamber, versus CH2F+. We form this by pulling chlorine off and ionizing it. And so these ratios are often things you see in the literature where they try to optimize breaking the strong bond versus the weak bond, including ionization processes. And so what I'm going to start with is to just take a look at this species and a little further detail down here on CH2IBR, and then expand it to the whole set to see if there's something systematic. So resources are important. We saw this in a very simple three-level model system I was showing you, and I'm not suggesting there's any quantitative relation between that and what this system is, but there's a qualitative connection. So this is pulling Br off of CH2IBr and recording Br+, and 100% refers to 100% of the laser energy, which is about 360 microjoules per pulse, pretty high. And this is the landscape, teched out point for point in the laboratory. These are the coefficients A, B, C in that polynomial phase. And 95% is declared as victory here at the top. And I think you can see there's two disconnected regions that are at the top. And perfectly consistent to have that. Now, when we pull back to 90%, see what immediately happened. This region, which was at the top, now has become suboptimal and became a trap. This region, which was at the top, has shrank to a small region. And if we keep pulling further, you see this pulls away as well, and so forth. And you, I think, remember the analog of this. I'll show you together in a minute, what we saw in a simple system. So what I'm going to transition now to, just as a side point, is two photon absorption problem. I showed you actually the landscape expressed a different way yesterday. This is a standard process. Two photons come in, one photon of twice the frequency comes out. There's A equals C, and the top of the landscape is known to be A equals B equals C equals 0. We're at the center here. That's the so-called most intense bandwidth of the pulse. Now you can't see that because it's hidden by this green yield. Blue is 20%, green is 40%, so it's sliced and opened out. And there you are at the top. So this is a known intensity-driven process. That's why I'm showing it to you. It's an intensity-driven process. And now let's come back to CH2IBR. Now what are recorded are several fragments in the mass spectrometer, the ABC. Here's CH2Br+. In other words, it's pulled off iodine and ionized this species. There's its landscape. Here's CH2I+, its landscape. And you'll note the very evident similarity between this known intensity-driven process and these two. That's telling us qualitatively it's very likely that these two species are driven by a hammer. Simple intensity, not something sophisticated. On the other hand, Br+, I showed you in this landscape before, is very rich. Does not look like an intensity process. And I+ also, in fact, looks similar to this, but also doesn't look like it's intensity driven. Now, the reason why this is important in this literature, there's a large literature on selective ionization of molecules. Many labs look at this sort of thing. And in the recent literature, this is what they have published. In fact, the optimization of CH2I+ versus CH2Br+. This is picked because it's convenient signals to record, and this corresponds to breaking the Br bond, ionizing this, and breaking the iodine bond, and ionizing this. Therefore, this is a measure of the ratio breaking the strong bond to the weak bond. And by optimizing it, they got a factor of 2. Well, you look at the papers, a couple people have done this, they're kind of happy with the 2, but other people have grumbled. Only if factor of 2, the theory says we should do much better. Well, you can see why now, just from looking at the landscapes. They're almost the same. You're taking the ratio of 2 functions that are the same in terms of laser parameters. You can't do much. So it's not surprising once we understand the landscape where this comes from. Or even taking dr plus to I plus, which is the ratio of these 2 landscapes, doesn't work well. However, if we pick the ratio of this landscape to this one, which is equally good as a measure of strong bond versus weak bond, remember we had to break the weak bond to form CH2 Br plus, the ratio is about 45. And the message for this community interested in this, although nominally all of these signals are expressing the same thing about breaking the strong bond versus the weak bond, they are completely entangled in the linearization process, which clouds what's going on. And so this is just a good example of where landscape principles have shed light on the physical processes taking place in selective fragmentation. So what I'd like to do now is just pull it all together, compare some things here. So we had the chemical reaction cases with catalysis, nice landscape. We had the same thing for bromine, different problems, climb to the top. Resources are not limited, everything's hunky-dory. We now start restricting the resources. Remember, we had this 3-level system where we have a closed trajectory at the top of the landscape, pull back on the energy resources, it fractured, pulled away. And that's exactly what we saw in this much more complicated molecular case, from here at the top to pulling away. So let's come back to this. Remember, we posed this question. And what I just got through walking through was pointing in one molecule in this array over here. So we'd like to look at the schematics of this. And once again, we fall back to the chemist operating principle is don't look at one molecule. Don't look at one green bar, or one yellow bar, or 3 of them. Look at the whole picture, because the whole picture is where the story is. So it takes a lot of experiments to do this, but we did it. And this is what we saw. We've not published this, but we were startled by seeing this. So let me explain how this was done. So let's start in the corner here. There's CH2Cl2. A photonic reagent called PCH2Cl2 was found that optimally pulled off chlorine. And then it was applied to every other member down this road. And there's the signal. And then, for example, the next one, CH2Cl3 is on the diagonal here. This photonic reagent optimized that, and then we applied it to the others. And that's how this was made. The diagonal elements are special, and then we applied it to all the others. And yes, there are aberrations, but it's dramatic. There is clearly a systematic pattern to this. And a key question is then, well, how do we order these things? So they actually permutation game. Basically, all we ordered them with their polarizability. We would pick some other electronic characteristics, ionization potential wouldn't change much. And this is saying there's probably a very simple story behind the chemistry. Now, it would suggest there is chemistry of photonic reagents, schematics of the subject. And this has some bearing on theoretical calculations. So in this table, in the published literature, there's about 3 cases that have been published experimentally before and have been studied. And the typical study in this area, theoretically, or by simulation, it's a 5-year study. It's very expensive. You have to do electronic structure calculations with many geometries and dynamics. A lot of approximations are made. It's very, very time consuming. So it's just not possible to say, look, we're going to do all of these cases with 5-year efforts. I'm not denigrating spending the time to do that. But as now the ability expands out to look at larger and larger numbers of physical systems with photonic reagents, there's an enormous drive to find models to describe what's happening. And if each model is a 5-year effort, you're not going to get models. But this suggests there's something simple going on in these problems are 10 to the 10th states accessible at the energies that are being pumped into this volume. Okay? So let me make just a general comment here. So this is material science and chemistry alone. This is photonic reagents and chemistry. So here we started with a particular bottle of stockroom and found and shopped in the photonic reagent stockroom. And we went to another bottle of stockroom. Well, of course, we can play all of this game collectively, although no one has done this, and unleash everything here. There are robots to do chemistry. We talked about that. They're just shopping in the chemical material stockroom. There are robots to do shopping in the photonic reagent stockroom. There's no technological reason except expenses and complexity for not combining this together, and there's ample reasons to argue it would be interesting to do, just making high value on your optical materials, making an example. So let me just end up with this picture. When I say end up, I have a little more time. I want to just expand this a little further. But so this is, in fact, a picture of 1/3 of the laser laboratory at Princeton. And oh my God, I told you about the 2 years and 20 minutes experiments. In fact, the flavin experiment I showed you, if you remember before, those 2 flavin molecules, took 5 years to do that experiment. 5 years and 20 minutes. 5 years to get all this right, and 20 minutes when you push the button. So this is complex, and this is like, as I told you before, like 1950, you wanted a television, you bought all the parts and soldered them together. This is not all canned up. And there's the lasers in the back, but that's only part of the story. And all of this is necessary. This is a modern chemistry and material science laboratory. In fact, the first thing that is very evident comparing these, this is far more automated. All the loose parts have been, for the most part, put in boxes. And that's because this is a very high value area and people have spent the effort to engineer it. What you'd call traditional chemistry is kind of relegated to the hood in the background. The other comment about this is there doesn't look like there's any relation between these areas. But what the message I'm trying to get across is under optimization, and that's the key, under optimization, there is a connection between these areas apparently through their landscapes. Random experiments here have nothing to do with random experiments here, but optimization experiments show pattern, and that's evident in the literature. So let me draw a conclusion from this. So we think these landscape principles provide a basis to understand optimal control experiments, photonic chemical reagents. There's a lot of careful simulations now on the photonic reagent side that are supportive of this principle being valid. A major challenge is to understand this boundary, very complicated boundary between the nice world where everything is hunky-dory, no traps, and where things break down. We do not know if there's going to be a generic analysis of this. I'm somewhat skeptical, but there may be some general principles. It's too early to say. So I put stars in the last 3 things because I think they are practical implications already coming from this. Some on the laser side, some not. So if you go into the laser lab or into the chemical materials lab and you see traps, you start doing some experiments, you start seeing traps in the landscape, that's an immediate warning that something's wrong because they shouldn't be there. Now, maybe you picked a target that's unreachable, but the most likely problem is you don't have the right resources. And that has very high value applications, perhaps the photonic side, but certainly in chemistry and material science. To walk into a synthesis effort that may cost millions of dollars trying to find a high value material, and after 3 months you can say, whoa, there's something wrong with this problem because there's traps in it. People may start, may stop, may continue if they want, but the principle behind this provide a basis to give a warning. There are clearly already applications of very practical grubby, if you want to call it that, in the chemistry materials area that are showing some interest in it. And the principles come from what we started to learn on the photonic reagent side, and it may well be what we learned from quantum control, from landscape principles. principles may have a major legacy outside of that domain. And then back to rules. So this is the flip side of seeing traps. In fact, you could define rules. There's been no definition of rules in chemistry or other areas, really. Rules are systematic driven. And so you could define rules as a minimal set of variables that give a trap-free landscape. If that's an operative principle, you can make a robot, in fact, look for that. It's a pretty dreamy sort of statement. But are there questions? I'd like to move on just to talk a few minutes if I could. Yeah.
So when you say that the presence of traps indicates an ill-posed experiment, is that an ill-posed control experiment? Or
Yes.
Is it, okay.
Absolutely not. Any experiment where you can do something and record a signal is okay. But I'm talking about ill-posed optimization experiment. I'm trying to think the best. Okay. Other questions? So if I could take maybe 10 minutes, if I could do that.
That's fine with me. Yeah.
Okay.
Go ahead.
So what I'd like to do is cut this off, and I'm going to restate some things in another set of views, and expand it out further. And I'm really stepping out over the edge of the table here by doing this, but what the hell, right? We follow our nose around, as I said. This is another talk, and I will give you a little piece of it. And so, even in the laser side, quantum control, I mentioned to you at the beginning, people are beginning to study, think about control within the nucleus, and that's, timescale 10 to the minus 24 seconds, 10 to the minus 8 centimeters, and all the way up. So there's vast timescale, certainly even in the quantum side. But now we fold in chemistry, maybe beyond, one can consider, are there common principles really over a larger swath? And again, under optimization. I'm strictly talking about optimization. So first question is, where is optimization encountered in the sciences? Well, of course, quantum dynamics, chemical material science, and now I'm going to include what's called natural evolution, natural biological evolution, and directed evolution. So what's the prescription except for natural evolution? You pose an objective, you arrange for the relevant control variables and seek an optimal solution. All of these things are posed this way. Directed evolution is the engineering harnessing, I'll explain it a little bit later, the engineering harnessing of evolution to change living systems for our own human purposes. So where is optimization found in the sciences? Everywhere. So let me quickly run through these. I already went through this. I don't have to say much of anything about this. There's control within quantum dynamics. You know the story. Shaped electromagnetic fields. About 200 successful experiments ranging from, let's say, satisfactory results to excellent. Typically, it takes 10,000 or 1,000 to 10,000 experiments, the order of minutes, to pull this off. But the space is the size of 10 to the whatever I wrote down here, 100 times. Astronomical, yet repeatedly we see the same thing happen. So I'm after this common theme, and you'll see this now. And this is how this is done on the photonic radiation side. It's really a robotized laboratory set up to automate this process. You saw this table before. A lot of things are going on. Not too many experiments in either area, so we only begin to see the systematics. We don't know a lot about mechanism. The rules are just beginning to be seen. How quantum this is open in many cases, but it works pretty well. So through. Let's move on to B. Optimization of chemistry and material science. We've done talking about that. So chemists optimize synthesis, yield, and properties. Basically what we do. The controls are chemical, solvent, catalyst, processing conditions. And it's safe to say that chemistry is widely successful. And let me show you a table here. Another recent paper we published that looked at this subject in some detail in the chemical material side. And these are references in that table. And first, let's look at this column. There's a number of variables. These are all robotized experiments. And I'll show you a picture of a robot in a chemical laboratory in a moment. And you can see immediately that chemists don't deal with, material scientists don't deal with 100 or 300 variables. They deal up towards 30, 5, 10, 30, that's sort of the range. And they do all kinds of things. You can see all kinds of reactions, you name it, versus with on. And these are results taken out of the literature, not our work, other people's works. And these are the number of experiments these people reported for getting very good results. Right? I'm not going to question. They said they got good results, they passed the referee process, okay, I accept it. And you can see immediately the numbers. They're not 1,000 to 10,000, they're a few hundred. Repeatedly so. Now, the last column is the number of experiments reported in these papers that their machine could have done. So in other words, the first one, after 300 experiments out of 6.4 times 10 to the 7th, they got perfect but good results. They got this number because they digitized the settings on the various conditions and multiplied it out. Now, some papers didn't report the numbers. But here's one, my favorite one is this one. 8 variables. These guys were trying to make a semi-permeable membrane such that something would go through it. And after 192 experiments, they got good results. And here's the number they claimed their machine would do, and I believe that's true. 9 times 10 to the 21. You know, 9 times 10 to the 21, as if the difference between 9 times 10 to the 21 and 10 to the 22 is of any relevance here. I think it speaks to something. And let me show you a quote out of this paper. The study parameter space at 9 times 10 to the 1 from a possible combination, a total of 192 polymeric solutions were synthesized, producing a substantially improved membrane performance, period. No comment. Now, in fact, I could find you very similar quotes in the later literature. People say the same sort of things, except this number is more like 10 to the 400th comment. So no comment. I mean, this is really a surprising statement. So here is an example, a picture of a robot. It's hard to see this, but you have a lot of little vials. It's a stock one, and they take aliquots out, move them around, move some reaction vessels, shake and bake, and so forth. So it's very similar to laser experiments. And as I told you before, chemistry is driven by rules. And a very fundamental question is why there are any rules at all. And I gave at least what we think is the answer to that. So let me move over to natural evolution. Now, what I'm going to say here has been observed by many people. Many people. I'm sure you've thought about this sitting in Starbucks and saying, oh, you know, how the hell do I exist here? You know, after a billion years of evolution, and it shouldn't happen. So the issue is fitness landscapes of populations of species. You don't look at one bacterium, you look at an ensemble of them. And in the evolution literature, the notion of landscape is around for a long time. So people have been thinking about this for a long time. So what are the controls? And this is a dangerous word to use in evolution. Control brings out all kinds of kooks when you talk about evolution. So let's use that word because we know what we're talking about here. So the number of variables referring to the number of sites on the backbone of the genome. And there's about 1 billion sites. Each one of them would have 4 values for the nucleic acids. So the truth is, the number of variables that Mother Nature can play with is 4 to the 10 to the 9th. Larger than the number of atoms in the universe. So first of all, there's no question that Mother Nature is playing with a full deck of cards. That's a very different story than when we go into the chemical stock room. We've got 1,000 bottles to choose from, not 4 to the 10 to the 9th. The operations for turning the knobs are mutation and crossover and insertion, or deletion, dismutation, various types of operations on the genome. This is certainly not a gradient algorithm by Mother Nature. This is a stochastic insertion of some form. So what are the experimental findings? Well, first of all, we exist. And evolution is surely a continuing process. And the surprise that many people have observed is, how did this happen? It's a question, because it shouldn't have happened, given this complexity. And even one protein has an astronomical number of variations in it. How did this happen? This is an interminable argument that this is always, it's all over in the literature, in the bioevolution literature. But what's relevant is not looking at, we believe, not looking at the genome of a rat or a mouse or a dog because they're frozen in at least human time scale, but to look at what are laboratory experiments in microorganisms, because those are real laboratory time scale experiments. And the reason is that bacteria and viruses turn over very quickly. And one generation of human beings is 8 years. It takes a long time to do an experiment on experiments. And as we know from the flu, viruses evolve very quickly from month to month. So there are some experiments that have been running for 30, 40 years, and they've run through 40,000 or 40,000 generations. That's longer than human beings have existed on the Earth. And they do experiments that we would call pump and probe. They call disturb and observe. So they take the genome and they disturb it. They make a mutation and watch the population evolve and see if it comes back to the top of the landscape, so to speak, or they change the environment. And the findings from these experiments are mainly the following. They generally find global fitness convergence. In other words, you disturb the system, it comes back to this global optimal fitness. They see genotypic diversity and global optimal fitness. All that says is the top of the landscape is flat. Just as we've seen in quantum control problems in chemistry, there are multiple solutions at the top. And most importantly, they see lack of what's called reciprocal synaptostasis. One of the problems with biology, you guys don't like chemistry, try biology. The language barrier is pretty hard. This language says they don't see traps. A reciprocal synaptostasis would be a local hill on the evolution landscape. It's very rare that this has been seen. So the findings here are really consistent. And lastly, is directed evolution. This is a human effort, using bacteria, to try to re-engineer them to make chemicals or drugs. This is an industry that exists, it works. Same genomic variables. And here's a quote from one of the field, Francis Arnold at Caltech. Recent work shows that an evolutionary walk can go in quite interesting places. So that's a very benign way of saying it works. So in this area, again, this is a laboratory exercise at engineering and biological level. There's a picture out of a paper in 2011. And you can just stand back and see, the closed loop. It's the same thing we do in the laser lab, except they do it with biology here, with cells. Same game, automation. So let me put all this together for you. And I'll leave you with a thought. So here's a table that covers everything we've talked about. We basically have talked about these two things in detail, but there's a large, we could talk for another hour about all of this stuff too, large literature here. But this arranges these topics for completely diverse areas, vast length and time scales involved, no question. What the variables, control variables are, what's optimized, the outcome, mechanism understanding, systematic, laboratory implementation, and just go across the quantum side. We use photonic reagents, yield or fidelity is what's the objective. Outcomes are, say, are good, sometimes better, good is fair. Mechanism understanding, not too much, but we're beginning to see something. And some rules are beginning to emerge, and this is certainly automated. So what's common here is not all the details of what these things are, but these comments at the bottom. The libraries of controls in all of these cases are exponentially large. Yet the number of experiments to reach optimality is generally an infinitesimal fraction of that. And so, here we are with the question that I've been trying to give the answer to, or we think the answer is, why is good fortune? And we can express it as a series of questions. So are the common features in that table, or other similar tables in the sciences, greater than the differences? Or is it a coincidence? Or in fact, should we just ignore it? People do laser control experiments, whether I said anything about landscapes or not, we do chemistry experiments without me saying anything about landscapes. But here there's this body of literature that's flashing about the really shocking efficiency of these experiments and very similar behavior, so is there a unified picture? And what are the practical consequences of that? Well, we're suggesting there is a unified picture, but I don't know the practical consequences.